Kia ora Year 12 and 13. This is a scholarship Conics question from 2008. I should warn you that this is going to be quite a long video. I can't see much way around that, so hang in there and try and break it into small steps. The first part of the question is really easy, kind of, I don't know, merit level 3. But the second part is mainly algebra, so it just goes on for quite a while. So the first thing we're asked to do is to find the Cartesian equation of this curve here. So x is equal to sec theta minus 1, and y is equal to 2 tan theta plus 2. So I suggest you go and have a go at that, and then you keep on going with the rest of the question. And it goes like this. The normal at the point P, where, and I'll just write the extra bits in, theta is equal to pi on 4, meets the curve again at point Q in the region where x is negative. Find the y-coordinate of Q in the form A over B, where A and B are both integers. Okay, so I've just written that in shorthand. Okay, so once you've got that Cartesian equation, I strongly suggest that you do a little graph, sketch what you're looking for, and I'll keep going on the next slide. Okay, so let's start with a nice easy bit. X is equal to sec theta minus 1, y is equal to 2 tan theta plus 2. So just we're heading towards a hyperbola equation. We can get it easily if we rewrite this as x plus 1 is sec theta. And over here, first of all, y minus 2 equals 2 tan theta. And now let's divide both sides by 2 to give me tan theta. And the reason, of course, that I want to do that is that sec theta minus tan squared theta is equal to 1. So what I'm going to do now is I'm going to square both sides of both equations. And call this equation 1 and this equation 2. And I'm going to do equation 1 minus equation 2. Right. So x plus 1 squared minus y minus 2 on 2 squared. Well, that's the left hand side done. Is going to equal sec squared theta minus tan squared theta, which equals 1. So over here we're going to have x plus 1 squared minus, writing this into my standard form, y minus 2 squared on 4 will equal 1. And I'm going to pop a 1 there too. So you can see that we've got a hyperbola. Now a squared is 1 and b squared is 4. So obvious things to think about here. Well, we're going to look at the centre. Not asked for all of this, but doing a good sketch is going to help a lot. So negative 1, 2 will be the centre of my hyperbola. And the vertical asymptotes are going to be at y equals plus or minus 2 over 1, right? So b is 2 plus or minus 2 and a is plus or minus 1. Right, so it's going to be a fairly steep asymptote. So on the next slide, I'm just going to sketch what we've got. Okay, first I'm going to do a sketch as if we centered it at 0, 0. And we can put in the vertices here at negative 1 and 1. And I want my asymptotes to have a slope of 2 and negative 2. So there's 2 there. Right, so I'm going to draw in a really rough sketch now. There we go. You can graph this on your graphics calculator, but I'm doing this at home so I haven't got the emulator technology in front of me. So that's my really roughly badly drawn hyperbola. Now in the next question we are going to try and find a normal somewhere on that curve. So we're going to find a point where theta is equal to pi on 4. That's going to tell me where is point P on the curve. So P could be here or it could be here, so we'll work that out next. So once we've got P, what we're looking for is there's the equation of, there's the tangent line. So suppose P's here, then the normal line is going to come out like this. And what the question's asking me for is, where does this normal line hit the other bit of the hyperbola? Now, depending on how well you've drawn it, it might not hit at all. But I've just made up a point P here. So obviously it was a stupid point to pick because it doesn't hit the other side of the hyperbola. But you can see, suppose P turns out to be down here, then there's my normal line. And if I extend, so I'm going to get the equation of the normal line, then I'm going to extend it out and I'm going to find the intersection with that hyperbola. Okay, so for some of you, that picture will give you a strategy to solve the problem, right? So the next step is to find P, right? It's a bit like finding Dory, right? Find P, which is where theta is pi on 4. Then get dy by dx, and then get the gradient of the normal, then get the equation of the normal, and finally find the intersection of those 2 points, right, of the normal line with that one there. So we're going to start on that now. Pause again and go and try and do as much of that on your own as you can. Alright, so first let's get P, find the point. So x is equal to sec theta minus 1, y is equal to 2 tan theta plus 2. Right, so x is equal to sec pi on 4 minus 1, which is equal to 1 over root 2. Okay, because it's cos minus 1, so that's equal to root 2 minus 1. Don't turn everything into a decimal. Y is equal to 2 times tan of pi on 4 plus 2, which is equal to 2 plus 2. Right, remembering everyone, special triangles there. Right, so there's my special triangle. So y is 4. So P, the point on your hyperbola, has got these coordinates. Right, the next thing to do is to get the gradient of the hyperbola. Now the other thing I've just realised is that the hyperbola I drew on that last slide was not the one that had been shifted. So that was the basic hyperbola. That was sec, x equals sec theta and y equals 2 tan theta. But our hyperbola is going to be shifted back 1 in that direction and up 2. So it's got a different centre. Okay, anyway, so here's my point P. Now I'm going to differentiate the function, and I am going to use the chain rule on that. Okay, so chain rule and parametric differentiation. So dy by dx is equal to dy by d theta times d theta by dx, which is equal to y dash over x dash. Right, so y dash is equal to 2 sec squared theta, right? Remembering that y was 2 tan theta plus 2, okay, and x was sec theta minus 1, so x dash is equal to sec theta tan theta. So we've got the two components, now we've got to plonk them in together, and we get dy by dx is equal to 2 sec squared theta over sec theta tan theta, which is equal to 2 sec theta over tan theta, so that's over sine theta there and cos theta up there. Right, so sec theta times cos theta is just 1. That's very messy. Right, never mind. Better than nothing. So dy by dx is equal to 2 over sine theta. So that's good. We can work that one out. And at pi on 4, that's going to equal 2 over 1 on root 2. I think I'm going to do a new slide. Okay, so when theta is equal to pi on 4, we've got dy by dx is equal to 2 divided by 1 on root 2, which is 2 root 2. So the normal gradient is going to equal negative 1 divided by 2 root 2. Okay, so one thing that's good to do here, we haven't done complex numbers yet, but it's often a nice idea to rationalize the denominator. Sorry, the word's not coming out there very well. Rationalizing the denominator means I'm going to multiply the top and the bottom by root 2. And so you see that the denominator is now a lovely round 4. So we're going to work with this. So that's my normal gradient. Okay, so we've got P and we've got the normal gradient. Now we're going to write the normal line. Then we might stop for another graph. So P is at root 2 minus 1 and 4. Normal gradient is equal to negative root 2 on 4. So y minus y1 minus 4 equals m times x minus x1. Right, so be careful here. It's going to become that plus 1. Okay, yuck, a fraction, so we're going to times that through and get 4y minus 16 is equal to negative root 2x plus 2 minus root 2. So, now what? Well, we know where we're going is we're looking for, so we'll draw our hyperbola again. Hyperbola's been shifted back to here and it's got a centre here. So this is at 2. So we know it's negative 1. So they're my asymptotes, which really should be dotted, but they're not. That one there, and that one there. So let's draw the hyperbola in, roughly. So there it goes. Again, you can do that on your calculator. Now, we have found that my point P is out here, and it's up here. And now I'm getting the equation of my normal. And I'm looking for where does it hit over here. What's the y coordinate of where it hits? So I'm looking for the intersection of my hyperbola with my normal line. So where I've got to is I've got my equation nearly finished for my normal line. And I'm going to want to sub that back in to the hyperbola line. So we get this. 4y is equal to negative root 2x plus 18 minus root 2. So I'm looking at this and I'm thinking, oh, I'm doing quite well here. I can get y. So y is equal to this. Right, and I'm going to take that and I'm feeling quite good and I'm going to chuck it into here. Right, but this is just an example of where reading the question really helps. If I do this, if I substitute in for y, I'm going to get the x coordinate, and I'm not asked to do that. And we know it's going to be messy. So what I need to do is, instead of making y the subject of the formula up here, I need to take a step back and make x the subject of the formula, and then I'll get a whole lot of y stuff over here to substitute in. So we're going to rewrite it as follows. So we get negative root 2x is equal to 4y minus 18 plus root 2. So x is going to equal what? Well, let's see. X will equal negative 4 over root 2 y plus 18 over root 2 minus 1. And again, we're going to clean that up by rationalising the denominator. So x is equal to negative 4 root 2 . So what I'm doing there is that. Right, so I'm just multiplying through by 1. So some of you will be able to go faster with that step than I just did, but most year 12s, you will need to have a good look at this. Right, so this is negative 2 root 2y plus 9 root 2 minus 1. So now we're nearly there. So that's my x, and I'm looking for the intersection with this. So here's my hyperbola equation. Right, well, x plus 1 squared is going to be negative 2 root 2y plus 9 root 2 minus 1, and the plus 1 are going to go. So that's very, very good. Right. Minus y minus 2 squared on 4 equals 1. Okay, let's just rewrite that. So we have got, before we head down that big path, we had this. So that equals that. I'm going to get rid of my fraction again. So 4x1, x plus 1 squared, minus y minus 2 squared equals 4. 4 times negative 2 root 2y plus 9 root 2. I've got a plus 1 and a minus 1, so that's gone. Minus y minus 2 squared equals 4. Right, you should all be able to go from here. It's just algebra, you end up with a quadratic formula. So expanding that out. First, let's get rid of that. So it's going to be 4 times, well, negative 2 root 2 squared is going to give me 8y squared. Then I'm going to have take away 2 times 2 root 2 times 9 root 2 y plus, when I square this, I'm going to get 81 times 2. And then it's minus y squared plus 4y, right, multiplying that by 2 and then by that, plus 4 and then times negative 1 minus 4 equals 0. Alright, so we get 4 times 8y squared minus 72y plus 162 from that first bit, minus y squared minus 4y, sorry, plus 4y, minus 4 equals 0. So expanding out, I'm going to get 31y squared minus 284y plus 640, and that equals 0. Finally, I get to the quadratic formula, and I do this. So we get 284 plus or minus, right, yucky big number, grab your calculator. And you can do this, but, well, you can do the discriminant certainly on your calculator. But again, decimals are not much use to you in scholarship exams. So 2a is 62. So if you follow that through, you get y equals 284 plus or minus, so this thing here turns out to be 36 squared. So it's that over 62. So y is either equal to 320 over 62, which is the one we're after, or 248 over 62. So we should be really happy, really happy at this point, because this equals 4, right? And we know that that's true. Okay, and so this one here is my final answer. Y equals 160 over 31. Now I'm not going to use another slide, so here we go up here. So y is equal to 160 over 31. A is equal to 160. And B is equal to 31. So the normal meets the curve here, right? That's the y coordinate we're after. Alright, that was quite a lot of maths. So thanks for watching to the end, and make sure that you can go through and follow the logic for each step. Thanks for watching.